So welcome again to our tutorial. It's amazing that you're all here and really, at least time zone wise, I think truly global. So thank you for making it here at odd times for some and perhaps at better times for others. And hopefully this tutorial will be useful. My talk follows on Matthias, and you'll see a few things that Matthias already touched upon extensively, and I'll just repeat them. My objective is to talk more specifically about how we implement density functional theory for chemistry and material science. So I call it materials and molecules here in FHI-aims, based on something called Numeric Atom-centered Orbitals. You can see that my name, if you haven't seen it, is Volker Blum, and I'm at Duke University in the US. So for me, it's the morning here, a sunny morning in North Carolina. If you want to know more, find us online and see where that is. But it's a very nice place to be. And the other thing you see on this first slide is a radial function. This is actually a radial function, a 4s radial function of a copper atom, and that's what it looks like. And especially here near the zero, you see very strong wiggles. That's an all-electron valence radial function. And so these are the kinds of basis functions that we use to do all-electron theory in FHI-aims. So let me come to the introductory part of my talk, though, and you'll see that some things Matthias already mentioned. I will mention it again, perhaps in slightly different form or briefer. The one thing that Matthias stressed, and that I'd also like to stress, is that as FHI-aims, we have a very large community of contributors right now. Without those people, we wouldn't be who we are, right? So this is truly spectacular. The beginning of the code happened in 2004. And that was something I think decided between Carsten Reuter, Matthias Scheffler, and myself. It happened at the Fritz Haber Institute, where I was for that time. And so since then, a lot happened. The direct contributors to FHI-aims are about 150. So the tutorials that we have for the code, and this has been also a sequence of hands-on workshops over many years, with which I think some of you are actually familiar. They keep being developed. And so for today's tutorial, the people that actually specifically contributed to the GitLab repository, which you can see online, are Sebastian, Said, and myself. And people who tested include Jakob Filsa and Mohamed Nakayi, but I think there may be more, and I hope I didn't forget anybody. But thank you very much to everybody who contributed in general to creating these tutorials over the years. This is, again, the list of contributors. As Matthias said there, with absolutely certainly many more. These people here were all important in some way, and some of them extremely important to the development of the code. And so thank you for being here, and hopefully this continues. I think we have a great community. How we're organized is, as Matthias said, FHI-aims is licensed through MS1P, which is a registered nonprofit organization, and the objective is support for basic science. And if you've seen the registration process, which you have, then Ames Club is really something we use for registration, but the main community vehicles at this point are the Slack channel. As of yesterday, that had 430 users, and also the Ames Git server, which is really for everybody. This is not a development server only. It actually has wikis, build instructions, an issue tracker, and many more things. And so the number of users are 483. This is nice, given that we only started this Ames Git server maybe 2 or 3 years ago, as we did the Slack channel. And so this is not even the whole community that actually is there. It's just the people who actually joined. And in addition, the code has a broad ecosystem of connected infrastructure around it, and many more than I'm mentioning here. I'm just mentioning the atomic simulation environment, IPI, the PhonoPy code for phonons, FHI Vibes, which builds on some of these pieces and does phonon and initial molecular dynamics calculations as well. GIMS, which is a graphical interface, and I'll mention that in a second if you haven't seen it yet, and various other tools that have been developed by many people, including library tools such as those in the CCAM electronic structure library that we built upon. So why FHI-aims? Originally, when we started, the vision was, I think, really to have a tool for quantum mechanics-based simulations of real and complex molecules or materials, and, well, in principle, all of their properties, as much as we can program, without any a priori precision or accuracy limitations. We know the theory behind, and so that was also one of the reasons to go all electron, because that's a way to, if we can afford it, which it turns out we can, get rid of approximations if we don't want to make them. Given that there were a number of questions on core electrons before, I will say that we do have a working frozen core approximation if one wants to work with that at this point in the code. But we don't really need to use this. That's, in a sense, an add-on. The all-electron functionality works quite well. So that's the key algorithmic choice that we made. We also wanted something that allows us to deal with non-periodic and periodic systems on exactly equal footing. The basics of how to do this will be part of today's tutorial. And we wanted something that scales to large systems. And the scalability in practice, I think, goes up to thousands of atoms, because that's the range of calculations people do. Although it's not at all impossible to do more. That's something that one could try. It's a matter of programming in FHI-aims, but it would be possible, I think, to go much further, as others have demonstrated in our community. And that would be possible. Thousands of atoms is really the range that I've seen as useful for practical simulations, which is probably why this is here. And the other thing is that we wanted something that was computationally seamlessly scalable. So Ames should work on my laptop, and should also work on massively parallel high-performance computers, and it does, and or new high-performance computing architectures. I won't speak much about those today, but there is a GPU version for NVIDIA for some of the functionality we have, and following up on high-performance architectures that come out is an active development that we do in the code. And then finally, the key production method is density functional theory. Matthias talked extensively about this. But of course, beyond that, we also have correlated methods, in particular, in our case, things built around the random phase approximation or the GW approximation that are computationally more expensive, but that we'd also like to do. And to achieve all of this, the critical choice is the choice of basis set. That's the main thing I want to stress in this talk. So we use something called numeric atom-centered basis functions to expand the solutions of the electronic structure in the code. And that allows us to create accurate representations of occupied orbitals and densities for the all-electron case with relative computational ease. And that's what the code rests upon, that enables all the 5 points and more that are listed above here. All right. So one example of what the code can do, I picked here because it was recently done in our group together with several others, I should say, in practice. We wanted to do semiconductors with hybrid density functional theory for large systems. And so the key prerequisite that we need for this type of calculation is a high precision atomic structure as input, so we know where the atoms are. This is, in this case, what the experimental colleagues could give us to an extent, and then we have to fill in the rest. And then the objective were energy band structures for large systems, and in this case, the supercell, because it's a defect-containing supercell, was of the order of 1,500 atoms large. And so how do we do this? Well, we use semi-local density functional theory, for instance, the PBE functional, as in today's tutorial for smaller systems, with a van der Waals correction. For the semiconductor in question, you'll see why that is necessary and useful. For the structure, to make sure all the atoms are in the right place. And we use hybrid density functional theory, including in this case spin-orbit coupling, because heavy elements are involved, to calculate energy band structures. And so this is what the system really looks like. The actual practical calculations were done by Yi Yao and Gabriel Cognati here at Duke on a supercomputer of the National Science Foundation. So this is a 1,500 atom supercell of a bismuth-doped hybrid organic inorganic perovskite. If you know what this is great. If you don't know, you'll see that there are inorganic layers here and there are molecules in between. And this is really a crystal of which one can determine the crystal structure with X-ray diffraction. And so this is a high precision calculation, no tricks. And this can be done if you have a large enough computer. I think this was probably several thousand CPU cores of an Intel system at this point. So it was a supercomputer, but it's not one that is unattainable. And you can see that the bismuth atom that's situated here actually gives you a well-separated state from the conduction bands of the host crystal. And so this is quite successful. We're actually quite happy that this kind of thing can be done. And so this is one of the strengths of the code. Another challenge is usability. And so this I wanted to highlight here too. If you set up this structure here, with a text editor, this is great, but if you're not very good at scripting, you will have an atom that's in the wrong place and you'll do the expensive calculation, it'll be useless. This kind of thing can never be minimized, but at least we can try to alleviate the pain in a way that is sensible. What we can't get around is the constraints that be on existing supercomputers. So they work with queuing systems on the command line for security reasons. And so it's very difficult to computer of your choice and that the administrators will let on there. The standard way is different. But we can make the analysis of input and output files easier. And that's what GIMS is for, a graphical interface for material science that we'll be using for the tutorials also, which at this point has a few simple apps, in particular a structure builder. The structure builder can be edited, but more importantly, it allows you to see the structure while you're building it. And you don't have to install anything for this. It's based in a web browser. You go to the website and hopefully it'll simply work. At least that's what it does for me. And if you want to know more, there's a Journal of Open Source Software article here. It supports more codes than FHI-aims. At present, there's support for the exciting code in there, but this is a tool that we hope to be open for the rest of the community as well. All right, so this talk, I have to get a timepiece in front of me. Sorry about this. I'm going to talk mainly about how to solve the Kohn-Sham equations. Matthias just introduced, so I won't say much about the foundations of the equations, but I'll talk about technical concepts and importantly the basis sets which give us high precision. I will say a few words about especially spin-orbit coupling, so relativistic effects, about integration and grids. And if I get to it, scalability. There will be a separate tutorial, however, in the series that will be focused on large-scale calculations later. So steps in practice to electronic structure theory. That's what we rest upon. Matthias summarized this extensively. The equation that we use looks like this. It looks like Schrödinger's equation. It's really Dirac's equation that we should be solving. And in practice, every code solves a particularly relevant approximation to Dirac's equation for their particular needs. That contains everything we need to know about materials and molecules. The next step that we usually do is we separate electrons in nuclear coordinates. So we make the Born-Oppenheimer approximation, explained by Matthias. And then we address the electronic subproblem, which consists of a kinetic energy term for the electrons, an effective electron-nuclear interaction, and an effective electron-electron interaction. This is not yet density functional theory. It's the full many-electron Hamiltonian. And we want the energy for a given set of atomic positions. And then usually we go on and build some higher level methods on there. So that's what we're going to be focusing on. And I'll go through this quickly because Matthias mentioned this before. There are two ways of achieving this. You can either go directly from the wave function, which you just saw, or you can use density functional theory, where the key part is the exchange correlation functional here. And there's the ladder of density functionals that Matthias just mentioned. So local density approximation is simplest. Our tutorials today are mostly going to be happening at the level of generalized gradient approximation, so PBE, and hybrid functionals, for example, semiconductor systems. There are meta-GGAs, of course, which is a very important development. And of course, there's also the many-body development that is very important to us, not only for reference, but actually it would be nice if we could use that at some point for productive calculations. People are working on that too. And then there's van der Waals interactions. For today, they will not be so important, but if you think of the organic-inorganic hybrid that I mentioned a few minutes ago, there the van der Waals interactions between molecules are actually critical, and they're not implicitly included in hybrid functionals or GGAs. And so you have to add them on in some form. And we also know how to do this when various methods that are precise and accurate are implemented in FHI-aims as well. All right, how to solve the Kohn-Sham equations. Here are the equations again. And almost everybody in the field will start by taking these solutions, the orbitals, which are continuous functions, and discretizing them into a finite set of functions. So we call these functions phi. There's a finite number of them, and we call it basis set. And then the approximate solution to the Kohn-Sham problem becomes a linear combination of basic functions. In our case, these are the numeric atom-centered orbitals, as you'll see in a moment. So what happens mathematically is actually quite simple. You pick your basis set. This we define as the Kohn-Sham Hamiltonian. We rewrite, just inserting this expression here into the red expression up there, we rewrite the expression into sums over these expansion coefficients that are here. Once you do that, you can integrate this whole expression from the left. This is invented in at least 1948, if not earlier, as the Rotan equations. You integrate from the left with another basis function, and you get a matrix equation. So you get a Hamiltonian matrix, an overlap matrix. This is a term we'll actually occasionally spot in the code, and eigenvalues and the coefficients of these eigenfunctions here, which are called the eigenvectors. That's what we do, and the only choice left, the only thing left then is to solve this matrix problem, which is now finite dimensional, and so we spend some time computationally on solving this matrix problem with matrices that we have defined, as you can see here. No, sorry, my previous slide. As you can see here as integrals. We need to integrate and we need to solve matrix equations. That's what we need to do numerically. So in practice, the choice of basis functions could be almost anything. And we'll see much more about this in the following part. But there's a second piece, which is self-consistency. And that's important to appreciate, that the equations up here look nice and peaceful. What I'm showing you down here is a linear eigenvalue solution. So we fix the Hamiltonian, that's what I did, and we solve in one shot for eigenvalues and eigenvectors. But it turns out that these potentials here depend on the solutions. And so that means the right side here depends on the left side, but the left side depends on the right side. And this is effectively a nonlinear problem. And so what we do in practice to solve these equations is we want a Hamiltonian that gives us the solution, define the same Hamiltonian that we put in. That's called a stationary point or a self-consistent solution. And so Hartree, the first one to do such calculations numerically, already knew this. He came up with a method of the self-consistent field, and that is basically an iterative strategy, mathematically called fixed point iteration, but we do this. It's important to remember that we're doing nonlinear optimization here. And if we want to do this, we have to start with an initial guess somewhere, and then we iterate ourselves to the right solution. So we start with an initial guess, we update the density, we update the potentials from the density, we update the matrices over here from the potentials, and then we solve this eigenvalue problem and get an updated set of eigenvectors and eigenvalues out. We put these back in to build a new density. In here, we actually make sure that we keep the iterative process stable. This is known as mixing. And you'll see that in FHI-aims somewhere written out that we're doing mixing, and you can actually play with the parameters if you like, although the defaults that we provide should hopefully be sensible for a wide variety of calculations. And then you iterate this process to convergence until you really have a solution that yields the same Hamiltonian as input, which produces that solution as output. Right. Basis functions themselves. There are many good options out there. And so the choice, however, will impact everything you do later, because the functional form of these functions is seen throughout the code. So one widely used prescription in the community are plane waves, which have a simple mathematical form, but that came up before. They are actually not all electron in practice unless you manipulate them, because you need to integrate things around the nuclear region, which is very difficult if you keep the core electrons. So typically you take the core electrons out of that process. They also are inherently periodic because plane waves are periodic functions, and so non-periodic systems have a few extras with plane waves that also make these a little more tricky. Gaussian type orbitals are the other alternative widely used in quantum chemistry, mainly because you can integrate these functions analytically, and that makes for fast integrations. The problem is that here at the zero, a Gaussian function doesn't have the right behavior towards the nucleus, and so that alone can make for relatively large basis sets. The other thing is that the analytical form is not necessarily entirely helpful if the Gaussian becomes very extended, because you have to perform very extended integrals. But nevertheless, this is probably the most widely used prescription in quantum chemistry. There are many other prescriptions out there. One particular prescription that we often use for reference for our own calculations are augmented plane waves that are widely seen as the most precise, numerically precise methods if you can handle them in the community, except at the cost of being a little bit more complex to use. But what we use in FHI-aims is something called numeric atom-centered basis functions, which is a natural prescription that was also suggested early on. And so we did not invent this. Many codes implement this as well. So we knew that this was a good prescription for us to build on when we started the code. And so this is very simple. The basis functions are attached to an atom. So this function here would have an atom at point 0. The angular behavior of the function is given by an angular momentum function, so a spherical harmonic. And then the radial function here is flexible. Actually, what we use are tabulated functions that are splined. And so you could, in principle, choose any shape you like. In practice, we do choose solutions of a radial Schrödinger equation. So this is just the radial Schrödinger equation shown here. So these are the types of radial functions that we have in the code, although we're not confined to them. We could use others. And so this covers functions such as free atom-like, hydrogen-like, or Gaussian type functions. And importantly, is this term here, which is we can control the shape of the function using this potential here, Vi. But if we want to localize the function, we can do so smoothly by adding a cutoff potential at a certain radius. And this can be relatively far out. So this doesn't have to be a strong approximation. In fact, it shouldn't be. We just cut off numerical tails that are far away and should not contribute to a solution because other basis functions pick it up over here. So this can be typically 6 angstroms in our tight settings, 5 angstroms in our light settings. So this is far away from the atom for practical purposes. But that means that this function here goes smoothly to 0 at a certain radius. And so you separate the heavy, expensive numerical terms in different ranges of the calculation. And so this is a prescription that allows us to naturally include all electron basis functions because we can represent them as splined versions of, for instance, the core functions of an atom, or the valence functions of an atom, or any other functions that we want to throw in. So we get the behavior near the nucleus correctly with relatively few functions. And so the choice of efficient and of enough radial functions is of course important, right? Otherwise this method would not be usable. And so that's something we spent about a year on in the early days of the project to make sure that we actually were satisfied that we could converge to high precision. And so that led to a basis set library, which you'll see. This is encoded in the species defaults that will be used in the tutorials for all elements between z equals 1 and 102. And some of these basis sets are very light, and others lead to very high precision milli-electron volt level converged total energies if you want to use them. The construction of this list at the time was actually done for density functional theory using a computational algorithm that essentially picked basis sets, basis functions, good basis sets from a large list. The principle was very easy. The atomic occupied orbitals are always included as basis functions because this gives a good representation of everything that happens on the atomic site. And then there's a large pool of candidate functions, and you can pick functions one by one and minimize a trial energy using the variational principle to find out which basis function at a given point is the most necessary to optimize the total energy of a non-trivial target for optimization. You find that basis function, you add it to the basis set, and then you iterate until the total energy no longer goes down. And so it turns out that the the energy to be optimized for that was necessary for the basis sets we use now was a very simple one. It was dimers of the same atom. So for example, carbon-carbon or iron-iron or something like this. And so you minimize the total energies of non-self-consistent symmetric dimers at different distances for this pool of trial functions, which in practice are hydrogen-like functions or ionic functions. And so you can see that the energy error, which is plotted on the y-axis here, as a function of basis size, as you increase the number of basis functions you have, goes down rapidly to essentially arbitrary precision sub-milli-electron volt for this target. And so this gives you a list of functions. So this is a list from the original FHI-aims paper that just says, aha, for hydrogen, we start with the 1s function of hydrogen, but then the first basis function we add is a 2s function with a particular numerical parameter in here, effective nuclear charge of 2.1. That just defines the shape of the function. The second function is a p function, and it also has a particular numerical shape. And this actually follows chemical intuition. So this looks very much like quantum chemistry with Gaussians. You would also add an S and P function, except here the computer told us that that's what it would like to do. And so this gives you already a light but not terrible prescription for calculations. It's actually quite a sane prescription to do calculations. And so this would, we call this the first tier of basis functions because they're the most important one. And that's the tier 1 basis set that we use in light settings. If we want to go to tight settings, we add more basis functions. The computer gave us more on the construction algorithm that I showed you before. So an S function, a P function, actually another S function, and a D function. And so we call this the second tier because it goes one higher in angular momentum, and then you can go on. And so if you look into the species defaults later, which will be shown during the tutorial, this, for instance, is the species default for hydrogen. All these functions are pre-tabulated, so you don't have to reinvent them if you like. You can just copy this here into your input. But if you want to play with them, FHI-aims allows you to do that. And the way to play with them here is relatively simple. If you want more basis functions, you just uncomment more of them. If you want less basis functions, for example, for speed reasons, you can comment them out, and your calculation will proceed with fewer basis functions. That's all it takes. So it's a simple edit of the input file. Right. So we tested these basis sets in various capacities in the meantime, and we're quite happy with how they perform. Perhaps the biggest paper focused on reproducibility and density functional calculations in the solid state in our community was this one here, the science paper led by Kurt Lejaguer and Stéphane Courtenier in 2016. It has 68 co-authors from 15 different codes who tested all electron methods as well as 40 different pseudopotential sets at the time. And the metric they used to assess agreement between different codes is a very simple one. They would take the energy versus volume curve of simple solids as it comes out of a particular electronic structure code, and they would compare the shape of these curves. So the 0 here is fixed to be the same, no offset, but the shape would be compared, and that gives them a so-called delta, which is really just the least squares integral over this gray shaded area over here. And that tells you how much two different codes disagree in this basic quantities. And so it turns out that the tests weren't even done by us, but we happily ended up with our basis sets very close, essentially indistinguishable numerically with the other all-electron codes. So this is a precise prescription that actually works across 71 elemental solids in this case, so for a very wide range of test systems. We did more tests in a paper about a year later. There's a test against a very high precision prescription, so-called multi-resolution wavelets for molecular calculations with a benchmark set of 211 molecules. This was a test that was primarily focused on the total energy. So if you do DFT PBE, it turns out this is a total energy error here for the top plot that goes down logarithmically in kilocalories per mole. And for the NAO basis sets, light, tight, tier 2 and tier 4, you can see that this error very quickly drops below 1 kcal per mole for the total energy, not for energy differences, for that is even better, but you can also get to a factor of 10 lower if you like with a larger basis set. So you can converge this to what you need for a practical calculation if necessary. And finally, we did a similar test for electron band structures, in this case against linearized augmented plane waves. So I mentioned augmented plane waves before as the method of choice for benchmarking where we go to it. So this is gallium arsenide, the band structure of gallium arsenide as an example that will actually show up in today's tutorial as well. And so the red curves are mean to K, the blue curves are our results, and on this scale they're basically indistinguishable from one another. This is also an electron volt scale. You see very small deviations up here, and so we can actually address these deviations by going to a larger basis set. Although this is in the high-lying unoccupied states, and so for chemical bonding, these do not play a role. And in the valence range, there's really no distinction. We plotted this more systematically for 103 other compounds. So a list is given over here. And this just gives the deviation between valence bands in those 103 compounds. So each point here corresponds to a compound, and the x-axis is the highest nuclear charge that's in the compound in question. So it goes up to somewhere near lead and bismuth. And you can see that For scalar relativistic calculations, so no spin-orbit coupling included in this case, the deviation is essentially at the level of 10 milli-electron volts. In some cases, maybe a few tens of milli-electron volts, but not more. So this is essentially for band structure calculations indistinguishable numerically. And if you go to spin-orbit coupling, which I'll come to later, you see that different methods, especially for the heaviest elements, give you slightly different values. So this is a predicted spin-orbit splitting in PBE for those 103 compounds as a function of the magnitude of the splitting in APW. And what we use in practice in FHI-aims at this point, and that'll be in the tutorial today, is a perturbative approach to spin-orbit coupling. So that means we do a scalar relativistic calculation, converge that completely, add in add in the spin-orbit coupling operator to the Kohn-Sham solutions, and then just do a single shot inversion of the Hamiltonian for band structures that come out. And so for light elements, this is essentially on top of the, and for smaller spin-orbit splitting, this is essentially on top of the all electron results, which are, sorry, the APW results, which are given here as the dashed line. The FHI-aims results are the blue dots here, and you see that there's essentially no deviation. But even for the heaviest elements, where self-consistency in spin-orbit coupling does play a role, you can see that this perturbative approach performs quite well. So this is about a point something, 0.2, 0.3, maybe in this case 0.4 electron volt difference for the worst case. And so this is still well on par with the errors that we have in the density functional, but qualitatively, even for the heaviest elements, this works. I should say that we also have a essentially fully relativistic version of self-consistent spin-orbit coupling in the code that works for PBE and for closed shell systems. So you can get rid of these particular deviations up here if you like. But for practical purposes, this has actually been a very useful prescription for us for calculations, especially for large systems. I will say briefly what we can do for large systems and hybrid density functionals. This is a number of CPU cores here at the bottom, and time for SCF iteration at the top in 2015 for a gallium arsenide solid. We'll be using the smallest version of that, which is a 2-atom unit cell today for tutorials. But you can see that on a large computer at the time, even 1,024 atoms were actually quite feasible. So this is all electron and no tricks. So there's no use of symmetry to reduce the problem. This is really a calculation with all the electrons of gallium arsenide included. This is still slightly expensive. So at this point, I think we're probably a factor of 5 to 10 faster because of a lot of optimizations that went into the code recently. And this is an ongoing process. So this allows us to do the 1500 atom calculation that I showed you at the outset of the talk. And then finally, the spin-orbit coupling, of course, that also becomes relevant. And so here's an advantage of the non-self-consistent spin-orbit coupling method I mentioned together with the hybrid functionals, because that's actually quite accurate. And so that allows us to do a hybrid functional calculation for large supercells. So this here, as a different example, is an organic inorganic hybrid with 400 atoms per unit cell. And if you look at the components here, this is actually an organic semiconductor that's mixed with the inorganic semiconductor here. And you could hope for optical properties if the energy bands between the two components align in the right way. So here are band structure plots. So electronic eigenstates as a function of some path in K-space. Here's the calculation without spin-orbit coupling, and you see that the pink bands here, which are lead derived, are actually above the solid thin lines, which are organic derived for the conduction band. The band gap predicted by HSE here is 2.21 electron volts. But it's a semiconductor whose transitions lie between organic and organic. If you add in the spin-orbit coupling, you see that the lead-derived bands move below the organic bands. And so this changes the character of the material. The material is now, from a point of view of the prediction, very different, because the electrons, when they get excited, have to move between two different components of the material. And that is really critical. So leaving away spin-orbit coupling for heavy elements is not a viable option. It should be included. And I think for our band structure calculations, the option that we use actually works quite well, given the system size that we can reach. So this is just a quick illustration of what I said in words before. The quantum well that you build here, if you will, out of this material has the valence band on the organic blue component, conduction band on the inorganic red component. And so that's a type of quantum well that you also find in other semiconductor structures, but you can use these materials as functional materials. All right, I talked a lot. I think I'm probably a bit halfway over through my allotted time. We'll see how much I get further. But the most important point that I did want to make is that we do have a basis set library that allows us to do all these calculations. And so that that's something that can be used and will be used in the tutorials today and is available and hopefully very well tested so that, well, you can use it too. I'll interrupt here briefly to see if there are a few questions. I won't necessarily be able to take all of them, but if there are urgent questions, it would be nice to hear from you. Anyone?
We have one in the chat.
I am working on the chat. Let's see. How does Ames compare with the Wien2K code in terms of computing time? So for small systems, Wien2K uses symmetry heavily, and I think there we're somewhat similar. We don't use symmetry in our normal production mode, although there is a sub-tutorial on how symmetry can be included partially in the calculations if you want to keep it, because of course some instances that's important. So you'll find that on the tutorial side. So for small systems, I would say they're somewhat equivalent. My understanding, but please correct me if I'm wrong, is that FHI-aims can essentially do the large systems that I showed you for any kind of chemical composition. And my early experience with Wien2K, for which I have great respect, is that this becomes very difficult with the APW method. But people who develop in the APW space may have made more progress. My understanding is that in my personal use, the NAO prescription is really numerically much simpler to go to large systems, and that's why we can do this. Otherwise, we would have actually chosen APWs as a prescription when we started the code. That was a consideration. But I should say that I have great respect for APW, right? That goes without saying, because that gives us the benchmarks we want. Is there any way to calculate dipole moment of periodic systems, specifically molecules adsorbed on a surface? So for that specific case, the vertical dipole moment could probably be calculated unambiguously, the absolute dipole moment, because you have a surface and you know where the vacuum is. So in the Z component, you could do that. In practice, I believe even the output dipole functionality of FHI-aims does this if you localize the slab appropriately in the unit cell, because you can just calculate the dipole of the whole slab. In a periodic system that's three-dimensional periodic, the absolute dipole is not well defined. It actually depends on your reference frame, your choice of origin. And so that's a more detailed problem, which we can also solve. So there's something called Born effective charges in the code, and that goes to a different aspect that can be done with the code. But for a molecule on a surface, the answer is relatively simply can do. There's a question that can we say it's better than quantum espresso or VASP? So I have tried to avoid a battle of the codes, right? Because a lot of good work went into VASP and a lot of good work went into quantum espresso. And in fact, we work with all these people over times in our joint work, right? I think we have a few strengths where we actually can do things that others cannot do. And I think it's very fair to say that the others also have a few strengths that can do things that we cannot do. Although of course we're working on being able to do this. But I think if you ask for specific cases, in specific cases, I think FHI-aims actually has an advantage. The 1500 atom hybrid DFT calculation that I showed before, I haven't seen before. Maybe somebody else knows, but we use FHI-aims because because we can, right? Because it's actually possible. Great. Actually, I'll deviate from my script. Hopefully that's okay also for those who watch this online later, and answer the questions because they're good questions. Similar to Abid, could you comment on the benefits of atom-centered basis versus plane wave choice? I think computationally, both of them allow you to get at properties if you work hard. I think what is really simpler in our case is that the non-periodic systems, so molecular geometries, come very naturally. We can also use large vacuum spacings between surfaces for relatively low cost. Essentially, so we can use 4 to 8 angstroms vacuum between surfaces without a big deal. So we can separate these things better. The core electrons, of course, are a big thing because we can just represent them outrightly and we can be done with them. We don't have to deal with issues of pseudopotentials or PWs. So from a practical point of view, I think our methods are somewhat simpler for those things than the plane wave choice, which is why we went with that choice in the first place. We knew very well about plane waves. All of us came from the plane wave world. That would be my current answer. How is spin-orbit coupling included in the Kohn-Sham equations? I will actually say something about that more. But what I showed before were non-self-consistent spin-orbit coupling results. So we did a scalar relativistic calculation first during SCF, and then only a single cycle that included spin-orbit coupling. And so this is not an accident. In fact, that allows us for the hybrid DFT calculations to do the very expensive part of the hybrid DFT calculation without having to double the system size. And the non-self-consistent version of spin-orbit coupling then comes as an add-on. And so that makes the calculations feasible, especially the large-scale ones. And so this is a feature of the method, not a restriction. It allows us to do calculations that otherwise we couldn't. What I was surprised by doing that benchmark work is how reliable the method actually was. I hadn't originally expected that it would work that well, but it has worked very well for us. Yeah. Oh, in a slide, you compared the variance with other codes. I saw Wien2k is at the top of the list. Why? That's a good question. It's only there because I made it so. The Delta project itself is deliberately set up to be neutral with respect to the codes, and you can place any code you like at the top of that list at their website. Right. And so then there's a technical question, and that is something that should really be moved to our Slack channel or issue tracker, if you wish. But that's a good question because it allows me to say that. So thank you for the question. It's about convergence problems, force occupation projector, and whole localization during an XPS calculation. That really is a technical question. For this, we do have our infrastructure, and we try to answer there because this is not a trivial calculation that you're attempting. It can be done, but one has to discuss it. And then there's a question about relativistic treatment. This also goes to the tutorial later. For QM calculation intended to develop a force field, would you recommend relativistic treatment in Ames if the atoms we're dealing with are not heavy atoms? And so the answer is, I would always recommend scalar relativity. There is no extra cost. So the atomic Zora scalar version that you'll see in the tutorials, it has been very stable for us, the bedrock of what the code can do. There's no extra cost, but you avoid any, on the total energy level, any issue with non-relativistic methods. So there's really no benefit to using a non-relativistic calculation. I would always include scalar relativity because it allows you to go seamlessly to heavier elements. Thank you. Great.
I think there has been one raised hand, but it's been put down. Maybe the question has been answered.
Kisho.
No, I raised hand. No, good talk, Mr. Walker. Thank you for the talk. And actually, when we apply these aims to the particularly metallic systems, like if we take boron, for example, boron in any transition metal matrix, boron has only one p electron, like outer. So in that case, like my question is how accurate these aims when we're dealing in interstitials like the boron in transition metal.
I wasn't able to catch the latter half of the question. So can you narrowly repeat the question? I know it's boron and a metallic system, and something got lost in Zoom.
Yeah, how accurate Ames is while calculating the stability of interstitial and metallic systems, like transition metals.
There is no accuracy problem. So if you want to, you can converge this to the sub-milli electron volt level. So precision problem, I should say. Accuracy is something else, right? Accuracy is also the question of the physical approximations, the density functional you use, which spin state do you use for the transition metal and so on, right? So that's a question that goes beyond just the technical numerics. You have to make sure that you use a density functional that is good enough for this. But on a precision level, there should be no problem.
Okay.
Yeah. So that what I said is general.
Yeah. Thank you.
Great. Thanks. So I'll move on. I have about 15 minutes left, I think. But thank you very much for asking these questions. They're super useful. I'm very happy to hear them. I have more than I can say in the 15 minutes, but the slides will be online too, in addition to the talk. And I'll see how far I get. So really what I wanted to say next is a lot of math. So if you implement this method, which is, as you can see, feasible because we actually did it, you have to deal with math. And so you have to deal with certain objects. So for instance, numerical integration. I already mentioned this. This is just a three-dimensional integral. It has to be done. Electron density update. You actually have to calculate the electron density and you have to do this personally on a grid. The expression is here, but this expression can be expensive to evaluate. It can be the most expensive part for an LDA or GGA functional, just because you have to do a lot of numerical operations. Electrostatics, you have to deal with Poisson's equation. So this is the integral solution of Poisson's equation for continuous charge density. And so we have to think about this. Especially for periodic systems, this means we actually lose an absolute zero of our energy band structures. We don't have a reference level anymore. And so we have to work around this if we want to do that, to find out where there are energy levels. Relativity, I commented on, I can comment on this more. We do need a capable eigensolver, and we have an eigensolver that we actually were involved with the development with for many years too, together with the main developers of the method called ALPA. We do need to treat periodic systems. This is completely feasible, but we have to implement something like phase factors to represent Bloch phases more later. And then finally, for hybrid functionals, we have to evaluate the four-center Coulomb operator for basis functions. So these are basis functions that could be centered at 4 different atoms. And so it's just a lot of objects. This object here itself is not hard to evaluate, but you have to evaluate n to the 4 of them. And so that becomes a large number. So all this we need to do. And the rest of this talk will say how we do some of these things. And all this is open in the input files. You won't need to change much of this, but you could, for instance, change the resolution of the grids if you wanted to. Gulam.
Sorry, I'm Bas. I'm from South Korea. So currently I'm using I'm using FHI-aims. So I have some questions regarding, can we perform piezoelectric or ferroelectric polarization calculation using FHI-aims? And
good
the
question
second question is,
first question, good question for the Slack channel. I think Christian Carbonia might be able to answer this of Fritz Haber Institute. He's the expert. Second question?
Yeah, my second question is that how about when we perform XPS calculation, specifically when we move to the periodic systems? So in that case, is only working is the force occupation basis method. So we are facing problems during the.
Good question, but can I interrupt? That's also a question for the Slack channel. That's a question that should be asked there, because the people who can answer it best are actually there. They will be there. They will answer, right? The group has just worked on this and that I think knows best how to do this. They are there. So I would route the question to them because it's an intricate technical question, but it can be done. But that's what the Slack channel is useful for, right? Because then you actually have the people who've done the calculations and who can look at specifics. Okay, and my third question is that specifically I wrote in my chat. So when we have for example, as a gold surface and we have a molecule on the surface. So I know for the molecules, we can print the dipole moment in using FHI-aims. So absolute dipole moment and also in 3 directions, dipole moment. But I'm facing problem when we have a surface and surface has some molecules adsorbed. So it shows that the error. So this is we cannot find the dipole moment for the slab system. Yes. Using FHI-aims. again, that's a great question for the Slack channel because somebody knows how to do it. I actually also know, except I would reassure myself with somebody else that this is indeed true. But we do know how to do this, right? For the Z component only. For the Z component, the definition is unique. But so that's a question. That's why we do have the Slack channel and these resources. So this is also good for the people who are watching online. It's very important. So we do have a community, and so we try, right? We may not be able to resolve every question, but especially the more tricky questions, the Slack channel has immensely enhanced our ability, and also the Ames Git issue tracker enhanced our ability to actually address such questions. The code can do a lot of things, but it has a lot of well, ways to do this. And so that knowledge, we try our best to make it available. But if somebody already has figured it out, the community that we have is really, well, it's what keeps us going, right? The people that we have around FHI-aims are the people who keep us going, and they will answer there if they can.
Yeah, my just positive feedback is that I am also user of WASP, and currently I'm also using FHI-aims, and I found the FHI-aims is much more faster than the WASP.
Thank you.
Definitely they are different, the basis sets, but for the large systems, specifically when we have more atoms, so WASP convergence problem, they have slow calculations, but in FHI-aims is really very fast. So I really very happy using FHI-aims.
Thank you for the positive feedback. Thank you very much. I don't have a direct comparison. On purpose, I don't do it, right? And as you heard, I also have great respects for the developers of WASP, but I'm delighted to hear it, of course, because we worked hard for this, and many in the audience and many on that list actually spent a lot of time working on this.
Thanks. Yeah.
Great. So how do we do this? A few more minutes. Perhaps the one thing that you'll see when you use FHI-aims in the tutorials, or if you've already used FHI-aims, is what some people consider, I've heard unusual recently, which is that we keep our numerical defaults out in the open. We have species defaults. And so, for instance, the grids here can be specified. You can copy a species default file as a default into a control file. You don't need to touch it. It just has to be there. And it tells the code what precision to use. But if you want to modify, for instance, the grid density and you understand the grids, you can. And so this next part is a little bit about that. What's in there and why can you modify it? And so the integration grids in particular are important to understand because they are built for the all-electron case. And so one thing that is important near the all-electron nucleus is that things become very rapidly varying. I showed that on my first slide. There's strong wiggles in that copper 4s function. And we need to capture them with meaningful integration effort. And so this is known how to do this from the quantum chemistry community. So what you do always, of course, is you take the continuous integral and you discretize it into a set of discrete points. But these discrete points are not even spaced. So they're not given on even spaced grids because we would need far too dense a grid. And I know people who tried this. And that grid would not be computationally manageable if you just try an outright even space grid for an all-electron code. But fortunately, we don't have to do this. So Axel Becker, I guess, in 1988 pioneered a method that essentially uses atom-centered grids. So spheres of grid points around atoms. These points even overlap. And so that allows you to build grids that are very dense near the nucleus. I'm not showing these shells here, but they actually are there. And then they become sparser further out where you need fewer grids because things don't vary as rapidly. And that allows you to do integrations with very manageable computational effort. The details are here for a few examples. And you get maybe 10,000, if you want to be dense, 20,000 atoms per grid points per atom. For heavy elements, maybe more, depending on the precision you want. And you can scale that precision in the input file. And so there's one issue that confounded the community for a while, which is how do you assign these integration weights for areas where those two grids overlap? So they're called overlapping atom-centered grids. You need integration weights. And so, sorry, I forgot that I actually have the specification in here. So for hydrogen, I'm mentioning 24 radial shells around each atom here. That's specified here in the input file. You can actually double the number of grid shells effectively from those 24 to, in fact, 49, 48 plus 1, by using this parameter here, radial multiplier. So you can make the grid uniformly denser. This makes your calculation more expensive, but you can easily look at the precision. And then the number of grid points distributed on each of these radial shells is given by something called, well, angular grids. And within 0.19 angstroms from the nucleus, you don't need very many points on a shell, so 50. But if you go further out, so for instance, within 0.59 angstroms or outside, we use 434 grid points. But we could in principle use 770 grid points or 1202 or a larger number. These grids come pre-constructed in the form of so-called Lebedev grids. And so that's pretty convenient because you can specify your grid accuracy if you like. If you have doubts, you can just converge. The integration weights that I mentioned before have to be put in. And so there's a trick called partitioning of unity, which rewrites everything to atom-centered integrands. This is in principle an exact rewrite. So you create a localized partition for each atom. And at any given point, if you sum over all atoms, these partitions add up to 1. You can define these by so-called weight functions. These weight functions are these peak functions here. You normalize these weight functions over all atoms. And for diatomic molecule, this comes from the PhD thesis of Jörg Behler, by the way, this picture here. For diatomic molecules, you can then see that atom A will be integrated almost entirely. This weight function is 1, where atom A is. In the region between two atoms, both atoms have sort of equal grid weights, and then atom A goes smoothly to 0 and the integration of atom B takes over. That leads you to these integration weights here. And you can, in fact, use the same trick for, and skip this in the interest of time, for the electrostatic potential. You can also take the density and use the same partitioning trick to create localized density pieces. And for this, you can then use a multipole expansion. You see a multipole parameter, L Hartree, in the species defaults. And that multipole expansion will allow you to represent the electrostatic potential out of density pieces that are essentially exact and add up to the whole density. So this here adds up to the whole electrostatic potential. And that's a very straightforward and manageable prescription. We didn't invent this. Bernardelli implemented this very successfully in the demo code that we knew when we started to be a solid implementation of electronic structure theory. Axel Becker was actually, I think, the one who published this particular trick first. And for us, this has been one thing that really drove the code and pushed it forward. So I'm almost out of time. So I'll skip a few things. To say briefly, of course, we can do periodic systems. Some of these, the math is in here. The key point is that we need Bloch wave functions, and we can do that with numeric atom-centered orbitals. We need a case-based grid. You'll see that in the tutorials if you don't already know it. So essentially, you have to integrate something called the unit cell of reciprocal space for observables. And this here is a continuous volume in a space of crystal momentum or parameter K that you use according to the Bloch theorem to represent the Kohn-Sham electron orbitals and density. And so you just put an even space grid in the simplest case. That's the K grid prescription, FHI-aims, that puts enough divisions here to give you a good sampling of the Brillouin zone, and that allows you to perform this nominally continuous integration discretely with high accuracy. But you have to choose high enough values for these numbers M1, M2, and 3. We use 8 by 8 by 8 for the semiconductors today, but for many systems, for small systems, you might want more K points. For large systems, actually, this volume here shrinks, and you might need less K points. Relativistic effects, I just wanted to say that I talked about them initially. They do actually become much stronger as you go from very light to very heavy elements. So gallium arsenide is the example that will show up today, but I already showed you something that contains lead. The details are here, the Dirac equation in particular that we solve. There is a paper in 2021 where we actually go a little bit more into detail about how to solve the Dirac equation itself in a way that works for all electronic structure theory. It's called a quasi-4-component approximation. Today, I just wanted to say that we can also rewrite this Dirac equation to create an effective Schrödinger-like form. So this down here is a simple rewrite of this equation up here. This is a 4x4 matrix. Down here, we have 2 spin components left, which is what we typically have in scalar relativity. And we split off the spin-orbit coupling term in the way that is customary in the community by rewriting this thing a little bit more. The next approximation comes in when we actually make the zero-order regular approximation that allows us to write this in a scalar relativistic form. Essentially, that amounts to taking the left side of this equation here and setting this parameter here to 0, so the left side is the same for all states. If you have time later, look at the slides again in more detail, and you'll see that now we have a left side that's independent of the epsilon here on the right side. This needs a small correction, which is what we call atomic Zora, which is that we actually need to make sure that the potential we use in this kinetic energy operator is a fixed potential. So it's the potential of a free atom, this of a sum over free atoms, the free atom at a given basis function. And this prescription itself makes sure that the solutions of this equation above here, which contain the potential, don't depend on an offset, an energy offset of the potential. This here is offset free, and that allows us to generate stable total energies and energy differences from a particular prescription. And if you compare LAPW with a different scalar relativistic approach to atomic Zora and FHI-aims, you see that these curves for the gold dimer binding energy curves, which would be very different from non-relativistic to relativistic, but here they're practically on top and just reflect basis set differences. And then spin-orbit coupling I already talked about, but we'll be talking about gallium arsenide in the tutorials here. So the red curves here are spin-orbit coupled, the green curves are non-spin-orbit coupled, and especially here near the valence and conduction bands, you can see differences that are actually important for electronics. All right. You can see these slides later, and Victor Yu is going to talk more about this later. This is the end of my talk. Hopefully I convinced you that in principle we can use this as a prescription across material science and chemistry. It's a high precision and also accuracy and reliability all electron code. It scales very well with system size and on available supercomputers. We make a number of practical approximations to what I call here the full Dirac equation, which is density functional theory. We can also use many-body perturbation theory. I didn't talk much about response theory, but it was mentioned implicitly because that's relevant for piezoelectricity or the dipole question that came earlier. So we can also talk about that. Relativity is something we've invested in over the years and continue to invest in. And you can do a lot of calculations. I listed here dynamics. In fact, there's real-time time-dependent density functional theory working in the code as well. Thanks to the work from the group of Peter Kratzer, in fact, Joscha Hekele in his group who did that for a long time. And continued work goes into making this code and keeping it usable. This tutorial is one such approach. This code has a lot of functionality if you want to use it. Please use our resources that we offer, especially the Slack channel to ask. We try to answer. And the code base is, of course, being extended by many people as we speak. And again, thank you very much to everybody who contributed. Thank you all for being here.
Thank you, Volker. I think we have a few minutes for some questions, if there are. I see still a raised hand by Kishore. I don't know if, Kishore, do you have still a question?
Maybe not, but we have
If
two in
not,
the chat.
But Oscar Douglas,
Yeah,
what's your
can
question?
you hear me?
Yes.
So do you recommend to use different setting of tiers for the same atom? Sometimes when you work with the slab, sometimes you use, for example, if the whole slab is gold, use the bottom layer with a light setting, but the top one with other tiers. Can bring some numerical problem if you create a new species for the same element?
I don't think it'll cause strong numerical problems, although I haven't tried it for gold. In the meantime, as you probably saw, we have the defaults 2020, which are reworked species defaults. So there's a little bit more flexibility in that you can see light, intermediate, and tight species defaults. And so that gives you an additional tier for gold that actually works quite well in terms of intermediate. But there's no formal problem if you want to reduce the precision in part of your system. I will say that for gold in particular, and especially with the recent modification made by Yi Yao in the head of the code, the frozen core method does give some computational advantage, at least for larger slabs in the eigenvalue sorter. So that's something to be considered for relaxations.
Okay.
But there's no problem in modifying the species defaults if you want to. You just have to, of course, with any modification, you have to make sure that the accuracy looks okay.
No modified, just combine. For example, use no? Okay.
Same thing, test. Yeah, no problem.
Okay, thanks.
But if you find a specific problem, I'd be interested, right? So there can be subtle issues. And some things happen and you don't know about them. Like you suddenly get a charge separation in the slab. That happens in a metal, possible, right?
Thanks.
But I haven't tested this. But for instance, if you say you have gold and water, right? So let's say you want to have your gold slab with high precision and the water with low precision. There's no problem then mixing tight gold and light water can be done.
Thanks.
Yes. So let me see.
There's one question in the chat.
Jinkai?
Can we predict optical emission spectrum?
Yes, to an extent. So I would say there are two ways that are mostly accessible right now. One is what's known as the random phase approximation or independent particle approximation for semiconductors. That allows for band-to-band transitions to be reflected. However, it misses excitons. And so excitons are a problem because we would need a periodic beta equation formalism, and that's hard to converge by k-points. There is actually something like that in the code, but it's a work in progress. For molecules, we can solve, so for isolated molecules, we can solve the beta equation, and so we get excitonic effects. From there on, we also have real-time GDDFT, by the way, that can do that too. That's thanks to Joscha Hekele and Peter Chatzer. From there on, however, it becomes a question of what is in the emission spectrum, right? Some optical effects can be quite subtle and can require correlation. That's not trivial. Others are pretty straightforward. I did see one question higher up, which is almost all popular codes are using plane wave or Gaussian basis set. NAO is not so widely used. Is it because NAO have some big shortcomings that hinder it getting popular? And I think the answer to this is actually no, there are no shortcomings. In fact, before us, as I mentioned, there were a number of other codes that do this. And so the DMOL code, for instance, is pretty widely used, except it's commercial and it's in a product called Material Studio, but it's pretty usable otherwise. FHI-aims is equally usable if you know how. So there's no limitation in principle. This can just work. Then, in order of questions, can we perform structure prediction using FHI-aims based on XRD data? It's a good question what you mean. Yes, if you have XRD data as input for your calculation, that's great. Because you can actually use FHI-aims to post-relax. That gets you a little bit away from the XRD data in terms of lattice parameters. But if you have a complex material, it does have the advantage that it fixes issues that might be in the XRD. For instance, hydrogen-carbon bond lengths may be fixed by an XRD program, but they're not fixed at the right bond length. And so you can use an XRD input in FHI-aims and just optimize, and you get a structure that is much more reasonable in terms of CH bond lengths. Yeah. And I do have one more. Sorry that it's all answered in the chat, but hopefully that's okay. Why are numeric atom-centered orbitals obtained by fitting to data obtained from dimer specific? It's a good question. So they don't have to be done that way. You could create your own. You can also use Gaussian type orbital basis sets in FHI-aims. That's possible, although we didn't optimize the species defaults for those heavily. We use them mainly for reference purposes, but you can optimize and they work quite well. You can use Slater type orbitals. They exist and you can implement your favorite by creating an input file, your favorite Slater type orbital basis set. So we don't need to fit to dimers. So when I created these basis sets, I used dimers as a first optimization target because it seemed to me like one that needed to be represented first. I actually tested a few extras, such as clusters of different shape. but I found that I by and large got the same basis functions out. And so that's the point at which we tested a few other systems. And it turns out that the optimization of basis functions for the dimers yielded basis sets that worked quite generally. So we didn't find any large accuracy deviations, precision deviations. And so this is actually in retrospect, natural or reassuring thing, because you can see that the entire Gaussian community also uses basis sets that are optimized not for a particular structure, but they're supposed to work across a whole series of chemical environments, and they do. And so that means if something works for a dimer, a general basis prescription should also work for something else than a dimer. So if we couldn't create a system-independent basis prescription with a set of simple systems, that would be a deep hole in all of the atomic orbital methods that exist, including Gaussians, including STOs, so very widely used methods. And so the dimers actually turn out to be the simplest test system that works, but that's an empirical observation. Worked quite well. We could have done more, but it wasn't necessary. We tested. FHI-aims for QMM simulations of biomolecules.
Volker,
Yes.
before answering the next question, I need a short break. I will be back soon.
Okay. Hopefully we can go on like this. I'm actually happy about the questions. I feel like I'm talking and I'm reading the questions, but thank you for doing this.
I would close the lecture around 5:30, and then
Okay.
continue with the introduction to the tutorials.
Right. And I'm happy to answer more questions in some breakout
Yes,
room in the
but
tutorials.
the Zoom session will be open all the time, so you can ask questions whenever you like.
Yeah. So there is the question of QMM simulations for biomolecules, and in principle, this is possible. In practice, the embedding setup to the chemshell environment is something that one has to ask the people who've done this for details. I think that's really probably the biggest limitation, that the embedding method hasn't been used widely, right? But there is something of that sort for FHI-aims that could be used in principle, I believe. Can we perform calculation of mechanical properties for structures with varying temperatures? That is true. It can be done, and I think in Matthias's group in particular, this has been done quite extensively using molecular dynamics by people in the group. However, you do need to do molecular dynamics and a few extras to get the finer temperature parts right. So that's also a question that can be asked more generally in the Slack channel, and the relevant developers and people who've done this would be the right people to answer this in more detail. Hopefully the answer is truly yes. I believe so.
Then we have another raised hand by Ghulam Abbas.
Just I have very simple question. So is there any way to build multiple configurations of complex system, like we have the adsorb molecule on the surface? So, you know, there are so many possibilities to consider the molecule's orientation on the surface. So my question is there any utility exist in FHI-aims that one we can use to construct the multiple configurations of that complex system? So
not in general, not for what you're saying, although some people have written something like this. And so for this problem, I think the group of Mariano Rossi might have some better answers because they have a tool that has been used for this. It's called Fha Aims, and they did molecular conformations on a surface from a genetic algorithm-based search. So there is a tool, but in general, for the global structure optimization problem, the best thing to do is, well, if you can't find a script that gives you the geometries, write your own, because every global structure optimization problem is different. In some cases, you want to keep certain bonds fixed. In other cases, you don't, right? And what you want to fix in a particular simulation can be quite individual, in my experience. So this is why people typically use the dual way of writing their own script for creating their input geometries and then running FHI-aims for a set of input geometries. But I believe that for your specific question, there is an answer in the community, except it's an answer that one would have to ask to a specific person because they've actually developed this method.
Yeah, sorry, would you like to tell me the software name or package name which I can use to construct this kind of configurations?
For FHI, but you would have to talk to the developers because they might know a bit more how to use it, I think.
Maybe I actually don't know the name. If I know, I can learn by myself. It's no problem.
Yeah, but this is exactly what this is. Sorry that I keep giving the same answer, but this is exactly what we have our Slack channel and the Ames Git repository for, because then we can point you to the right direction very efficiently.
Okay, thank you.
So maybe let me clarify that. Can you see my screen?
Not yet, but I can stop sharing mine, and maybe that's
okay.
I can see Bastian's screen.
Perfect. So as you can see, there are two Slack workspaces. So most of you, I invited you to the FHI-aims tutorial series workspace. However, Said already shared the invitation link for our community workspace. So if you have specific questions, how can I do that? Is that possible? I encountered this problem and I have this particular issue. Then please use the link shared by Said and go to the official community workspace. This maybe is a little bit inconvenient, but it's for us better to organize, like the old principle, divide and conquer. So we will use this workspace mainly for the tutorial series. If you have general questions regarding FHI-aims, go to our community workspace FHI-aims and ask your questions there.
Yeah, and be gentle with the people there, right? So
yes,
I think it's very important to remember that we're not a company, right? In the sense that we're not, we don't have a large support department. If we wanted to do that, the conditions for FHI-aims would be very different, right? But we do this because we try. And most of the people in the Slack channel and the people who contribute to the code work quite hard, right? So if there's something that can't be answered immediately, it's not because we don't want to. It's because we're people like you, right? We're scientists. I do have another question, which is very interesting from Oleg Rubel in the chat, which I briefly wanted to answer.